I'm really happy that today's speaker is Professor Bernd Büchner. I mean, I know him for a long time. We know each other for a long time.
Yes.
We have been in many exotic locations, including a conference in a cruise, and we had many nice conversation beyond physics that time.
Yeah.
And so let me just get into more formal introduction. So Professor Bushner, who is a very well-known experimental physicist, and he has contributed in terms of pioneering work in the field of high temperature superconductivity, more recently on iron nictite, which will be today's topic of talk. And he has versatile interest in general in correlated electron systems and also on topological properties. And he is currently, in fact, since 2003, is the director of the Institute for Solid State Research in IFW Dresden. And he is also a professor for experimental physics at the Dresden University of Technology. And before moving to IFW, he was in Aachen University, and he graduated from University of Cologne and in the year 1993, and was habilitated in 1999. And I found that he is involved with various activities of DFG in various capacities with this long association. So with this very brief introduction, I welcome today's speaker and looking forward to your talk.
Yeah. Thank you. Thank you very much. Thank you. First of all, thank you very much for the kind introduction, for the kind invitation, for giving me the possibility to speak. And I apologize very much for the delay and for the trouble with these connections. Actually, I regret very much that I cannot visit your institute, that I cannot visit this very nice place, which is shown on this photograph. And I hope very much that this will change in the future. We have a lot of connections between these institutes. These are some pictures from our own place. So this is this Leibniz Institute for Solid State Materials Research in Dresden, so in the east of Germany. It's also a nice city, and I hope very much that we can do something together. Actually, there is a clear memorandum of understanding, some cooperation, and what you read here is a part of this. I took this out, that we really intend to cooperate on novel magnetic and topological quantum materials in the future, and then we really want to exchange people to do something together. We have already a nice collaboration also with SETI on photoemission, which I will mention also later. So, and I hope very much in the future that then we can really see each other face to face and not via this funny Zoom or whatever internet connections. So let me now move to today's talk. So I will not talk on topological materials. We can do that later on. I'll go back a little bit to my history, to, let's say, superconductivity, and I will show you some recent results which we had on iron-based superconductors. I will start with an introduction and discuss first the aspect of electronic correlations in these systems. How important are they? That's really controversial also still today. And then I will come to something which I personally like very much, and this is this aspect of orbitals. And I worked a lot on manganites, and where we also met in the past, where orbital degrees of freedom are very important in these oxides. Determine all these Jahn-Teller transitions, determine all the ground states. And something of these orbitals is also relevant in these superconductors, and it's connected to something which people now call nematic phase transitions. I will introduce these nematic phase transitions, and then I will move on to more recent things. So for the first time, we were able to prepare.
Just one interruption. I don't know whether you are changing your slides, because for us, we are on the very last slide. I don't know whether you are changing or you are not.
I changed the whole time.
No, but it didn't show up.
Oh man.
So maybe you can get out of your full screen mode.
No, for us, for me, I'm outside the network. For me, it changed.
Oh, it changed.
Yeah.
Yes.
So maybe it's a local problem because I'm outside the network, so I can. For me, it changed.
Hey,
So again, I try
nothing
once
is-
more. Now I change. This is now the outline thing.
Yeah, I can see it.
we cannot see, and also I think Manoranjan had that problem. So is it our local problem?
Yeah.
Yeah, it did not change for me also.
What can I do?
It is changing for me.
Yeah.
Can you please stop sharing and start sharing again?
Yeah, I'll try.
Yeah, and maybe we don't need the full screen. Sometimes full screen
Yeah,
is
yeah.
a problem.
I'll try. I'll try now. So now I stop sharing, and now I start sharing again. Do you see it?
Yeah, we see your desktop. I think we see your terminal, but not yet the presentation.
This one?
Yeah, now it has come.
And now, does it change?
Can you please? Yeah, now it. Oh,
Now
we
it
missed
changed.
all the nice pictures. Yeah. Right.
Now it changed. And if I go to full screen,
Yeah.
so does it change now?
No, it's not
Yes.
full screen.
No, yeah, okay.
I think
then,
I
does
think
it
the
work?
SNBO Center network.
Does it change
No.
now? Does it work now?
No. Is it full screen?
Yeah. One
No,
moment.
I think the full screen mode for some reason is not working, at least for some of us.
Does it work now?
No.
No, I have no full screen anymore.
Yeah, it is working now.
Okay. Yeah, it's working now. Can you go to the next slide?
Now I have the outline slide here.
Yeah, it's outlined.
Yeah, it's working now. It seems.
It's working now
Yeah.
for all of you?
Maybe I think you are not in full screen mode. Maybe that should be okay.
So I'm not in a full
Without
screen
full
now.
screen, maybe we can.
I'm not in a full screen now, and I'm.
Yeah,
Does it
maybe
work?
that's better. I think if you go to full screen, there is a problem.
Okay,
So like
so
this,
now
maybe you can.
let's try this. There are some things will not work, but the main things will work. It's no problem. Okay. So should I continue now?
Yeah, please. Yeah.
Okay, good. So I hope very much that we can avoid all these trouble in the future when we meet person face to face. So either in Dresden or in wherever it will take place. Okay, now let's go on to the outline. So I will discuss this iron-based superconductors. I will start with a short introduction, and then I will address this aspect of electronic correlations. How do we have signatures of electronic correlations in these materials as well? And then I will move to something I like very much, orbitals which are well known for oxides and for manganites, for example. But I will also argue that this orbital degree of freedom is quite important in these iron-based superconductors. And here it's often used the frame of nematic transitions or nematics, which is, to my understanding, closely connected to the orbital degree of freedom, which is still relevant here. And then I will move to recent things which are connected to the fact that we were able now, after a long time, to grow large crystals of these 1111 or lanthanum oxygen iron arsenide crystals. And we have revisited this phase diagram. We address the point whether there's connections between nematic fluctuations and superconductivity, and I will show you that also the normal state is very, very strange. So let's move to the beginning, and that's already 12 years or 14 years ago when these iron-based superconductors were discovered in this paper here by Kamihara and all, they saw that this material, lanthanum, oxygen, iron arsenide, shows superconductivity at rather high temperatures, nearly 30 Kelvin, when doping these systems with fluorine. And this has attracted a lot of attention. It was like a rush similar to that what happened in the cuprate cases. And there are just some newspapers shown here. And the reason was that after a short time, TC raised to about 60 Kelvin. So people hope that we really can come to higher transition temperatures. And of course, it was also the question, what is the mechanism? Is it a new mechanism? Is it an unconventional superconductor? So till today, there are a lot of efforts on that. There are many examples, meanwhile, of these iron-based superconductors, and that's just a couple of them, the most prominent one. You see these are the systems where superconductivity has been discovered. The characteristic feature in all of these systems are these layers here. We have iron arsenic or iron selenium layers in a tetrahedral environment, which we will have a closer look on later on. And in the initial compounds, between these iron arsenide layers, there were these lanthanum oxide layers. And this is a very special situation. So in some sense, we combine an oxide with a more metallic layer. And the other compounds, the other more famous compounds of these iron-based superconductors are more intermetallic compounds. So this complicated lanthanum oxygen layer is here replaced by simply a barium atom. So we really have in these 1 to 2 systems, and these are by far the most studied systems, we have a simple intermetallic compound in some sense. And for such intermetallic compounds, you can then grow single crystals, large scale single crystals. That's from our own work. And that's also the case for other systems like these lithium iron arsenide or sodium iron arsenide, so-called 1-1-1 systems. Again, there's just a lithium in between there, or even the most simplest one, iron selenium, where you have just iron selenium layers and nothing in between. So, and both of these are very famous as well. So you see, this is a van der Waals coupled system. This is a 2D system. And indeed, if you go down to the monolayer, which we are also now able to do, and others as well, there is evidence for high TC superconductivity or raise over superconductivity if you go to the monolayer. Also, these systems, of course, are very nice to cleave, because here you simply can cleave between these van der Waals coupled layers, or it's a similar situation here. We have lithium here, lithium there, you can cleave here. You have very nice photoemission data, which I will not discuss in detail today. We have a lot of data on this as well. So what I will go back to these initial systems, and these initial systems, which are to my extent very interesting, because they still have the highest TC. These are the systems we have to understand also. But they are, from the materials point of view, very, very complicated, because we have this oxide together with this whatever, intermetallic things. Good. So the first idea is when you see such a structure, such a layered structure, if you have active and non-active layers, that's very similar to a cuprate. Again, we have a layered structure. Superconductivity comes up upon doping, so we have to add in some charges, at least in most cases in these iron-based superconductors as well. But there is a major difference. So the parent compounds are antiferromagnets in both cases. So this is an example for this barium 1-2. You start from an antiferromagnetic state, you dope, and then superconductivity emerges. And that looks very similar to the case of the cuprates. Also, you start from an antiferromagnet, you dope, and then superconductivity comes up, and there's some more complicated stuff which I will not address. So very similar, but the ground state is very different. So the starting points here and there are very different. In the case of the cuprates, it's well known that they are strongly correlated. We have a Mott-Hubbard insulator, so that means that the electrons are localized at the copper sites and do not form a metal in the parent compound. And the reason are these strong correlations. So when this electron moves there, you have to pay a lot of energy, this due. And this gaps the system. So you have an insulator, you have a gap of 1.5 eV, and you end up with an antiferromagnet via the super exchange as depicted here. So that's prime example of a MOT insulator, these cuprates. And this is different in these iron-based superconductors. These systems, okay, again, as in cuprates, band structure predicts a metal. It predicts a metal where all orbitals, all relevant orbitals cross a Fermi energy. And this is also at least in rough correspondence to the experiment. So the parent compound are metals or bad metals. I will come to this later on, but they have a complicated Fermi surface. And this is also taken from some very early papers where you have, let's say, at the gamma point, you have some barrels here, and at the M point, you have some barrels here. So complicated Fermi surface. And then if you have these Fermi surface, at least in the parent compounds, the barrels have similar size. So you have something like a nesting condition, and this stabilizes a spin density wave. And that's the way how people discuss this antiferromagnetic state. So we start from a spin density wave, which is an instability of a metallic system, whereas in the cuprates you start from a MOT insulator. That's of course simplified pictures, maybe in both cases. So the first question which I would like to address here today is what's really a realistic description of these iron-based superconductors. So it's clear we are not in the limit of a MOT insulator like in the cuprates, but we also probably not in the limit of a very simple system where the electronic structure corresponds exactly to that what band structure calculations, simply DFT calculations predict. So what's going on there? And in order to address this point, we did photoemission spectroscopy. That's just a reminder. So we shine on light on the samples. Electrons leave the samples, and there is energy conservation and there's momentum conservation, at least for 2D systems. And this allows us directly to measure the band structure, to measure the electronic structure of these systems. And this is done a lot at our institute, and Sergei Borisenko is one of my group leaders, and there's a big machine which is located at a synchrotron facility where we can do the highest, among the highest resolution measurements of this technique possible in the world. And SETI was involved a lot in this, and we have a lot of common publications already in this, and that's one of our main activities. So let's have a look on one of these iron-based superconductors. And that's surprising. So this is now iron selenium. And what you see here, these are data measured for different photon energies. This helps us a little bit to fight with the matrix elements. This is a detail which I do not discuss in detail. So what the first thing is, yes, we have states here at the Fermi energy as predicted by band structure, but we also have something here at higher binding energy. And it turns out that this stuff, which you see at its higher binding energy, this is characteristic, and this is really some features which you can address to something that I would call a lower Hubbard band. And this comes from the fact that it's not found in these band structure calculations, but it is found in calculations where you model these electronic correlations due to the Coulomb correlations at the iron side, for example, by DMFT. This is just a comparison of these model calculations, so theory and experiment. So the message is, yes, band structure is correct. We definitely have these electronic states at the Fermi energy. However, we also clearly see these features which we expect in strongly correlated systems. So in some sense, our iron pnictides or iron selenides are located somewhere in between. So not very simple metals, also not clearly MOT insulators, somewhere in between, where we still see these features of the MOT Hubbard insulator, so this lower Hubbard band, and we see a renormalization, so the band structure itself changes, so the bands become flatter, the systems become heavier, as a name which you also know from heavy fermions. So that's also a feature of these correlations. So we have clear features also of correlations. And this is, let's say, my first very short take-home message. So these iron-based superconductors display both. They display these Fermi surface instabilities as predicted from Band's theory, so these nesting instabilities, but they also clearly really show the signatures of strong electron correlations. So in some sense, this ITC superconductivity occurs at this borderline between local and delocalized electron states. And that's not only the case in iron-based superconductors. It's also what people discuss in the cuprates. If you go to all these cerium-based superconductors, which are more strongly correlated, but also superconductivity occurs when you weaken the correlations. So it's quite characteristic. Unconventional superconductivity occurs just at the borderline. This is also the case, at least in my understanding, for these iron-based superconductors, where the correlations are, however, weaker than in the other unconventional superconductors. Now, the next question which arises from that is, are there signatures of local electrons? I showed you the signatures of the lower Tabor band from photoemission. What about spins? Of course, we have this spin density wave, and it turns out that the moments which you find there are larger than that what you get from simple band structure calculations or what you expect for a simple spin density wave. So already pointing that probably some local degrees of freedom play a role as well. And the next question then, what about orbitals? What do I mean with orbitals? So we have this iron atom surrounded by 4 arsenium or 4 selenium atoms. And if this would be a local state, let's assume that would be a localized insulator, then of course we would have a crystal field acting on these originally degenerated iron d orbitals. And in this kind of geometry, it's known that the EG orbitals, so those which are relevant for the cuprates with d x square minus y square and the z square orbitals, that they have a lower energy. And the T2G orbitals, named XY, XZ, YZ, have a higher energy. That's a typical crystal field splitting, and that's also expected for these iron arsenide layers. And if you look at the calculations, there's even some differences between here these different XY, T2G orbitals. But okay, in principle, this picture is fulfilled. Now, that's the starting point. And then we have 6 electrons. Okay, and you have to put these 6 electrons into these things. And then, of course, the first question is it high spin, is it low spin, and where to put these electrons? It's not clear. Of course, this would be the case if we have a localized picture. Then we probably would end up with a high spin state. Now we know that we are not dealing with this completely localized thing. We are dealing with this band structure. And indeed, it turns out that also the renormalized bands, which we have, still have an orbital character. But it's not so simple that there's one orbital which is clearly one band, which is clearly one orbital. They are intermixing and so on. And details are also not 100% clear. But it's clear that the electronic states responsible for transport, responsible for superconducting, somehow also have some kind of orbital character. And again, for orbitals, we know they are connected to lattice directions. They are strongly connected to lattice degrees of freedom. And that is also, let's say, the experimental signature in these iron-based superconductors, that these orbitals play a role, that we have an instability of the lattice. So this is, again, a very early data from a very early work. So we have this lanthanum oxygen iron arsenide, this parent compound. We cool it down, and then there are 2 phase transitions. You see here, for example, in the susceptibility, you see these 2 peaks. And the second one is indeed the magnetic phase transition. So muons then show a rotation. This is a spin density wave. And before we go in the spin density wave, we do a phase transition from a tetragonal to an orthorhombic state. So we break C4 symmetry at that point. And this is, in some sense, the signature that, okay, this is the reason for why we discuss nematics. That's the reason why I believe orbitals play a role. And this is now a phase diagram which has been put forward by theory colleagues. It's this barium 122. And there you again see this parent compound, which is magnetic. This is this blue stuff. And then you see, well, situation is slightly different, but qualitatively first, you also have a structural phase transition. In this material, it comes at the same temperature simultaneously. And then we also go to the orthorhombic phase. So we have this connection between magnetic states occurring in a close proximity to this structural phase transition. And these are some statements which I took from this paper, also 6 years or meanwhile. so that this nematic order, so this change, breaking of C4 symmetry in iron-based superconductors is a well-established experimental fact. And still the origin remains controversial, and that's still the case until today, and I will address this a little bit. But there's also another statement, and I think this is also meanwhile justified, that this nematic order is let's say, a new instability, which has been seen in clear fashion for the first time now in these iron-based superconductors, and now in the literature you will find a lot of examples where people discuss these nematic instabilities in other systems. So what's about the origin? Oh, sorry, that's now I have a problem. Sorry. So what about the origin? So this is, let's say, my attempt to bring this closer to you. So on the first place, we have this phase transition. We have this phase transition coming from a tetragonal lattice to an orthorhombic lattice. So that means lattice is involved. And if you measure, for example, the elastic constants, you see a softening of the lattice going ahead. So it's not only this phase transition, but there's some evidence for some lattice fluctuations. So lattice plays a role. And in this paper, we used NMR, a local probe of the charge distribution in this case, iron selenium and this material, to show that this phase transition goes ahead with a change of the distribution of charges within the lattice. And this was the reason that we argued in this paper that this phase transition is connected to orbitals, and actually it is orbital driven. Because in this iron selenium, this occurs without any magnetic order. And then we argued, okay, yes, we see this redistribution of charges. This points to these orbital degrees of freedom in a complicated manner, of course. And this is the instability. On the other hand, it's also well established that the magnetic order, which you have at low temperatures, so this antiferromagnetic order, is stripe-like. So you have this ferromagnetic and then the next stripe pointing in a different direction. So also this apparently breaks C4 symmetry just from the magnetic structure. And a lot of people argue that indeed this magnetic instability, this spin density wave instability, drives the system from a tetragonal to an orthorhombic state, drives systematic phase transition. So is it purely orbital? This indicated by the fact that it also occurs in systems which do no long-range order, or is it mainly spin-driven? And this is, for example, this barium 1 to 2, where the phase transitions come simultaneously. There it seems to be really a single instability. And that maybe it's still debated, and probably both aspects play a role. And there's another class of experiments which has developed then in these systems, and this is strain-dependent transport. And I will show you more data on that later on. So what you do there, you take a single crystal, glue it on a piezo crystal, and then you apply a tiny strain, and you measure how this resistivity changes. And if you would have a usual metal, that nothing would happen. You have tiny strain. But here, what you see here, even the slope, so the change of the resistivity divided by the size of this strain diverges. So you have this, and that's what people call nematic susceptibility, and the divergence of a nematic susceptibility. And this is now electronic degrees of freedom. So it's clear that lattice plays a role, orbitals in some sense play a role, magnetism plays a role, but also the electronic states. And that's the nematic order in iron-based superconductors, which is quite characteristic. And that's already the take-home message too, that we have this nematic instability as a characteristic feature of these iron-based superconductors. We have these three things: structure, magnetism, we have orbitals. And this means, I believe, that we have really an orbital-dependent electronic structure in these iron-based superconductors. And still, we have this question: what is the driving force? And the second question, of course, is it in some sense relevant for superconductivity? Can we find evidence for that? And this is, okay, the starting point for going back to these crystals. So that was a couple of years back. We found a possibility. It's a complicated process. It's a solid state growth process, which is depicted here, which then leads to these nice faceted crystals. So the first time now we could use this material there. We have this splitting, as I've shown you, between these two transitions, different from the other systems. So it's where we have two instabilities, and we can use this material to have a closer look on this nematic order. And this brings me to another point, which I have to address now. So these 1111 type compounds, so these lanthanum, oxygen, iron, arsenide, are somehow peculiar materials, not only from materials point of view, they are also from the electronic properties very different. So if you plot the resistivity, and this is the smallest resistivity which I think has ever been measured on the single crystals on these systems, you see a lousy metallic state, and you see even an increase here when cooling down. And then this phase transition comes, first the structural one and then the magnetic one, and then the strong decrease. The fact that we see the strong decrease means that this increase here is intrinsic. So we are really dealing with a bad metal. We are very close to localization in these systems. And that's different in the others, these intermetallic compounds. So this is a resistivity for lithium iron arsenide, which looks like a beautiful, beautiful metal. This is a special situation that you have these oxides in between, and that and the coupling probably is stronger. And that therefore leads to the fact that we are really dealing with bad metals. And you have really to dope these systems to make it good metals and have it becoming superconducting. And still, these are the materials where we have the highest TC, do not forget. So these are the systems which probably show the strongest interactions. And in order to highlight that they are really strange metals, even if you take a good superconductor, plug in a tiny amount of impurities, superconductivity breaks together. It's really very, very unusual material. Okay, this is the phase diagram which we have revised. First, we did that on polycrystalline materials. Again, fluorine doping is possible here. We see the phase diagram. We have these two phase transitions. So the nematic phase transition here, the magnetic one there. We have a decrease here of this nematic phase transition. We lose the signatures of the phase transition here. Magnetism disappears, and then superconductivity emerges. And already looking at this phase diagram, it seems that maybe superconductivity is not connected to, let's say, quantum critical behaviors of the magnet, but more connected to this nematic instability. But this is on polycrystals where we can do fluor doping. Unfortunately, even with our technique so far, we can only produce crystals where we dope with cobalt atoms. So we replace iron by cobalt. We know that these also lead to some increase of electron charge carriers, but it also leads to impurities. So it's not the best materials. We knew that TC, which we can expect, is much smaller. However, it's a chance for the first time to measure really a series of single crystals on that. And of course, we are currently working in our chemistry part to work on other systems with higher TC and fluorine doping, but it turns out to be very, very difficult. So let's have a look on this. So we can now revisit the phase diagram. We can do all these measurements. So we can use dialectometry to measure the structural phase transitions. So you see the orthorhombic splitting. It's large for the parent compound, becomes smaller upon doping. We can also follow the structural phase transition from thermal expansion measurements. We can measure the magnetic susceptibility. Where you see both transition first at small doping, and then you can follow these phase transitions. I will not go into details because we are already running out of time. This becomes superconducting later on at 6%. Reasonable superconductor, but TC is much smaller. That's what we expected due to these cobalt impurities. We also followed these phase transitions by microscopic probes. So this is NMR measurements where you can see for, let's say, 4%, you still have this strong increase of the relaxation rate telling you that you enter a magnetic state. Whereas if you go to higher doping, this peak disappears. So we have the border to non-magnetic state. So taking all these data, we end up with this phase diagram here. We have a lot of different probes. We have susceptibility, specific heat, thermal expansion, NMR, transport measurements. And then you see this is the nematic phase transition this is the magnetic phase transition, and this is the superconducting dome. And this, of course, is much smaller here. Tc is smaller, and the dome is smaller, and these are the cobalt atoms. These are the impurities. Okay, let's say we have to, the price we have to pay in order to do these experiments on the crystals. So let's have a closer look on these nematic transitions, on this nematic instability. And what I now present you is such measurements of the resistivity under strain. So we apply, this is a typical experiment, so you apply a strain and you measure the resistivity. And then you go back and forth, and then you plot the change of the resistivity as a function of the strain. You get these slopes here, you get these changes, and from these slopes you derive the nematic susceptibility. So the derivative d eta versus d epsilon gives you then this nematic susceptibility, and this is plotted here as a function of temperature. So, and it's not a surprise that again we see this strong, sorry if now I'm playing here, this strong divergence here at the structural phase transition. And now you can fit this by a Curie-Weiss law, which is shown here. So this is just in a different representation. You see this Curie-Weiss law. You see the Curie-Weiss temperature is slightly below, but close to this phase transition temperature. And this you can do now as a function of doping. So you always see this strong change of the resistivity upon tiny changes of the letters. We did that. Oh, sorry, now I'm again lost. So we did that for all these crystals, and you always see this Curie-Weiss-like behavior. You see that this Curie-Weiss temperature becomes smaller, approaches 0, close to 6% doping, and then it becomes even negative. So 6% doping is the system with the highest Tc. So if I now plot these Curie-Weiss temperatures from this fit as a function of doping, you see it hits the 0 just at the 6% doping. Just at the system which is a good superconductor, we have this, the fitting tells us, okay, this is the way where the nematic instability decreases, approaches 0, the relevant energy scale. What you get there from this Curie-Weiss temperature is, of course, the relevant energy scale for these fluctuations. You can do it also in a different way. So if you go back to the last transparency, you can also simply have a look on the absolute values of this susceptibility. And you see, if you go to overdoping, this susceptibility becomes much smaller than it is in optimally doping. And even if you go to underdoping, it becomes smaller again. So if you simply take the absolute values of the nematic susceptibility and plot that as a function of the cobalt concentration, you really have a surprise. So you really see two regions where this nematic susceptibility becomes huge, becomes very large. And one is connected to the concentration where the magnetic order disappears. So in some sense, what you see here is the coupling between this electronic instability and the spin degrees of freedom, which we of course expect, since this order, this magnetic order, is of stripe-like nature, it also breaks this C4 symmetry. The biggest surprise is that we have a second region here, which is very, very similar to our superconducting dome. So it looks a little bit that this region here is, let's say, mimicking this superconducting dome that we really have, and I think this statement is a robust statement. So superconductivity here appears in a region in the doping range where the nematic instability becomes quantum critical, where the nematic instability becomes very large as signaled by the large susceptibility, where the nematic fluctuations are very, very large. And this is, in some sense, the take-home message 3. So for the first time, we were able to measure the phase diagram of these doped 1111 systems on single crystals. What we find is that indeed that these two transitions, these two instabilities, the nematic instability and the magnetic instabilities, are well separated, not only in the parent compound by different temperatures, but also in the whole concentration range. We have a phase diagram with two quantum critical regions, one where the magnetism disappears and one where nematic order disappears. And the superconducting dome is clearly located at the quantum critical point where this nematic transition disappears, where the energy scale of the nematic fluctuations hits the zero. And of course, this raises the question whether superconductivity is really related to nematic fluctuations. And just looking at these crystals here, again, these are the systems showing the highest CC, these are the systems showing the strongest coupling between all the zero freedoms. If you just look at these systems, we would say, yes, nematic fluctuation seems to be very important. However, probably the situation is, of course, more difficult. And now I show you again some more elaborate work trying to understand this nematic instability. And it's also clear if we have these nematic fluctuations, there will be anomalous electronic and magnetic properties in the normal state connected to these nematic fluctuations. And one example is NMR. And that's maybe it's a little bit difficult, but I'll try my best. So these are measurements now of the relaxation rate as a function of temperature for different crystals, different dopings. So these are the typical magnets. If you have the magnets, you have this divergence. So slowing down of spin fluctuations, long range order, and then you end up with hit this blue region. And this you can follow as a function of doping, no problem. That's what you expect for long range order. If you then go slightly above this critical point, so here for this doping here, this strong peak disappears, but we still have a very, very strange temperature dependence. You still see this increase here of the relaxation rate. Even if you go to the best superconductor, you still have this increase of the relaxation rate, telling you you have a very unusual slowing down of magnetic fluctuations. So magnetism is highly anomalous here in this sense. And of course, the natural way to explain this is, okay, we have these nematic fluctuations here in this region, and we have the strong coupling to magnetism as signaled here, and this means that we also have highly anomalous spin fluctuations. So you could also argue, yes, superconductivity is occurring close to nematic order. However, we know that also spins really are anomalous in this region, and this could also be very relevant. Can we shed more light on that? And this, I will just mention that, of course, what you can do now is strain-dependent measurements of the NMR. You can really try to understand this coupling in more detail. We and also other people did that on barium 1-2, where the crystals are large enough. And indeed, what you can do here, you can really follow, on the one hand, these electrical field gradient, this orbital order as a function of strain, so you can induce this nematic instability, and then you can even induce magnetism, and that's just shown here. This is a relaxation rate as a function of this strain, and you see for some of the samples it increases, you see a peak, and it goes down at some temperatures. So you really induce now the magnetic order via this strain, and this is of course coming via this coupling, which is not a big surprise in these 1-2 systems where these phase transitions are strongly linked. And we are now trying to do the same experiments also for other systems and looking for better understanding what is really the role of this magnetic fluctuations if we have these unusual nematic fluctuations. And I have still a couple of minutes, so I will also show you other measurements which you can do. It's also a very exceptional situation. What we also did now is in order to understand in more details of the Fermi surface, or the anomalous Fermi surface due to this nematic fluctuations, we did measurements of transport coefficients like thermal power and Nernst effect as a function of strain. So we took again a piezo stack, glued the sample on top of that, applied a voltage, applied a heat temperature gradient, and measured the longitudinal and transversal voltages. And this you can do in a strained system and in unstrained systems, and from the difference, which is tiny, you can then derive the derivatives again. And the real first surprise is that there are really very clear changes upon tiny strain. So this is a typical experiment. So you switch on the heater, you have the thermal power here, you switch on the piezo, you strain the sample, you see a change here, goes back when you switch off the piezo again, and then the signal disappears when you switch off the heater. And this is at one temperature. You see, this is, let's say, the signal which we detect. If you do that at higher temperatures, the thermal power is negative, but the strain effect is still positive. And then you can plot the strain effect, so this delta S as a function of the size of a strain, get a straight line, and again, get something like a susceptibility. So this delta thermal power versus delta epsilon. You can do the same for a Nernst effect. So this is now the transversal effect. This is a system typically very small. And here you can even see these changes as a function of a small strain in the Nernst effect. And again, you have to do that in different magnetic fields as well. Then you get the Nernst effect. So message is, okay, even these more complicated transport coefficients, not only the resistivity, also even more complex transport coefficients, which are typically connected to the energy derivatives of density and mobility to time, and that means the difference between the mobility of electrons and holes or to details of the Fermi surface. Let's call it like that. Even these quantities show clear strain dependence. And this is now the Seebeck effect in the, without strain, in zero magnetic field. It is close to zero. It even changes sign, and that's due to the fact that number of holes and number of electrons are similar, and therefore we have this nearly zero, even this sign change. If you dope electrons, it becomes negative. Okay, that's what we know. If you now plot these changes, these strain dependencies, they do not show sign change. So in both cases, they are positive. So that already highlights the thing that probably these nematic fluctuations, this nematic susceptibility, are band selective. So holes and electrons react differently on the strain. So this is a question to theory. And we also see that here for the parent compound, this change is much larger than for the doped compound, and that's quite different from that what we have in the resistivity. So I think I'll skip a little bit the details. We can do the same for the Nernst effect. Nernst effect typically is zero in simple metals, but here in these systems we have a finite Nernst effect which changes a lot upon doping, and we can even follow these dependencies as a function of strain, these susceptibilities if you want. Again, you can get this Curie constant. That's easy. But you can also do a little bit more than the Curie constant. You can do an analysis, and you can discuss it in more details if you want. So you can write up that Seebeck effect is something which is connected to, let's say, the Peltier tensor and the resistivity tensor in the same way the Nernst effect. And then you can separate these strain dependencies in a Fermi surface changes. This comes from this alpha, and more resistive changes, scattering. And they are of similar size. So both things happen here. So people say that probably this X rho could be related to scattering, to spin degrees of freedom, but here most likely orbitals play a role. And you can even do a cross-check by measuring Seebeck effect and resistivity. We can put it up in this formula, and then we can reproduce the Nernst data from that. So if you want to see more details, it's in this publication. So this is the present situation where we are. So we have this new phase diagram. We have the nematic instability, which is occurring, which becomes very large, just at the same concentration range, where systems become superconducting. But it's not only superconductivity, it's also a lot of normal state behavior of these systems, which is very, very funny due to this unusual instability, which is connected, I believe, to the orbital degrees of freedom in this weakly correlated system. So let me give you some conclusions. So some take-home messages. That's the first take-home message, which I would like to bring to you, is that these iron-based systems are at the borderline between local and delocalized electron states. So we have electron correlations are relevant, less relevant than in cuprates, but they are clearly relevant in these systems. I've tried to introduce this nematic instability as a characteristic instability of these iron-based superconductors. I've argued it's clear that lattice electrons and spins play a big role here. They are strongly coupled, and I've argued that orbital degrees of freedom play a crucial role here. I've presented you this phase diagram for the first time with these two well-separated transitions. This is superconducting dome at the nematic quantum critical regions. And then at the end, too fast, I admit. I've argued that this pneumatic instability leads to very unusual normal state, very unusual metallic state. That's also the fact that we're really dealing with the bad metal, and that a lot of these properties are tunable by external strain. And this is really an interesting new technique now, which you can use to really to switch between the electronic states and this quantum material. Now, this I will skip, and these are at least I should at least mention the people involved in this work. I think basically all the experiments have been done in our institute, so it gives you some impression of what you can do within the collaboration. We can synthesize samples, we can do NMR measurements, we can measure these pneumatic susceptibilities, these strain-dependent transport measurements. The photo emission, which I have not shown here because it was not done on these systems yet, and we can do the magnetization in thermodynamics. And if you want to read more on that, this is a collection of the papers which appeared in the last years, dealing with just this series of samples which have been synthesized for the first time. And this brings me to my end. So thank you very much for your attention.
Thanks, Bernd, for such a nice and informative talk. Now the talk is open. Okay, talk is open for the questions, and Tanushree is already please go ahead.
Can you hear me?
Yes.
Yeah. First of all, thank you very much for your very nice talk. Unfortunately, with this internet issue in our institute, it got a little bit troubled. But and I'm looking forward to reading many of your papers. I took note of that. But I have two general questions. First of all, you talked about the effect of strong correlation, and it is in between being strongly correlated and moderately correlated. I mean, there is one, of course, among the theoreticians, very well-established concept that it is like a Hund's metal, and what is important is not the U but the J.
Yeah.
So experimentally, do you see any kind of evidence that it is, you can call it as a Hund's metal?
So first of all, I have to excuse at that point. Of course, I got this message from this comparison between the photo emission data and the calculations, the DMFT calculations, which have been done by Silke Biermann's team. Mm-hmm. And in these calculations, they also added the Hund's coupling. And you also can play with the Hund's coupling there, and you need it. So in that sense, I don't say that we can prove that's a Hund's metal, but it's clear that when you really want to describe in a correct manner the local degrees of freedom in this DMFT-like approach, you have to add this Hund's coupling. So sorry for that. So I was quick at that point, as I told that we are dealing with, in some sense, with a high spin system, and that means due to Hund's coupling. So Hund's coupling plays a crucial role. There's another aspect which is very interesting at that point. So I played with these orbitals, and I told that we have this renormalization of the bands, and that's of course well established from many ARPAS data on many different systems. But it's also clear that the renormalization is in some sense orbital selective. So you have some orbitals, the factors change a little bit. And this is also, the same company tells us that this is a consequence of the Hund's coupling. Yes, I think the concept is definitely well justified, and it's supported by experiment. But again, details are difficult. And this,
thank you. So my second question is how general is this phase diagram that you have drawn with this pneumatic phase? Is it only valid for 1111 compound, or is it valid for others?
So that's also a very interesting aspect, and that's also something which I don't know. I don't know that people really understand that. Mm-hmm. I began in the beginning with these 4 different prototype materials. Actually, there are some more meanwhile. And it turns out that not only the materials properties are different. So I've shown you one of the van der Waals system, one has this oxide in between, but also the phase diagrams are pretty much different. So we definitely do not at the moment have a general phase diagram. And I skipped these data at the end, so where we discussed lithium iron arsenide, which is, let's say, an example which really looks very much different. So we have these, I discussed these 1111 type systems. The 1-2 systems, electron doped, are, I would say, similar. Coupling is stronger, so the coupling between spins and this pneumatic transition is stronger. Therefore, transition comes at the same temperature, and the splitting is not visible. But I think there are good arguments that overall the physics is not so much different between these two systems. So, but if you go then to lithium ion arsenide, this evidence for the pneumatic transition is disappeared. So it's a parent compound which superconducts. The pneumatic susceptibility, whatever people measure, is much smaller. There's no magnetic instability, to best of my knowledge. No one has ever seen this striped magnetism in these systems, neither in the pure compound nor in the dope compound. And that's not clear. And still we have a superconductivity of still 18 Kelvin or something like that. And I think that's a big question mark. No? And I think, I don't think that people really understand that.
Okay, thank you so much.
Yeah, any other questions? In the meantime, I have, okay, Priya, yeah, please go ahead.
Yeah, sorry. Yeah, I just had one small question. So in the regime where your spin fluctuations are the strongest, are you saying that there are several competing magnetic states over there, and there is no long-range magnetic order? Is that what is the...
Very good question. And again, I can now give another talk on that. These competing magnetic instabilities is also a very important concept which has been put forward by several theoreticians for iron selenium. And iron selenium is another material where we have the pneumatic instability completely decoupled, or at the first glance completely decoupled from a magnetic instability. And there people argue that we really have two competing different magnetic states. The stripe-like states is competing with the checkerboard-like state. In my case, and therefore it's interesting to do that. So if you have this, let's say, magnetic fluctuations without any magnetic order, these competing states leads to some frustration, is a very nice concept. And that's discussed in the case of iron selenium. For these lanthanum iron-based materials which I present today, I think it's a different story. So we have the magnetic instability which leads to a normal stripe-like magnetism at low doping. And then we suppress this magnetic order, and we still have this pneumatic instability. We still have a situation where the orbital degrees fluctuate, slowly fluctuate. And whenever these guys fluctuate, the spin exchange, the difference of the spin exchange between the two directions also fluctuates. So we have a new channel, a very unusual channel of slow spin fluctuations coming via these orbital degrees. That's what I believe at the moment. And this is seen just in the optimally doped compounds, and then it disappears only if you suppress the pneumatic instability.
So in your case, when you talk about the orbital, degrees, controlling it, do you mean that locally the strain in different regions is inhomogeneous, and that's what is giving rise to this effect? Yeah,
whether it's really strain or whether it's just on the basis. Imagine you have these pneumatic instabilities. You have a local, you have this C4 to C2 transition, and imagine you do that on a single unit cell. That's what I mean with fluctuations. You have this instability. You can have it long range, fine. But above the transition or in doping regions where this long range order does not occur, we have these fluctuations. So, and you're right, locally, this means you have local fluctuations of the strain. Yes, in some sense, it's also because we cannot decouple that from the lattice. That's clear, because these orbital degrees of freedom are always decoupled in the lattice. Again, story becomes, then people argue we have the ions, which are much heavier than the electronic degrees of freedom. And therefore, people say there is a decoupling because the ions cannot follow and so on. Also, there is some indication for that. If you derive these coupling constants from these Curie constants from the pneumatic instability from electronic systems and from the structural degrees of freedom, there are some differences. And people say that this is due to these different velocities. I cannot tell you, but in some sense, you're right. There will be a local variation, local fluctuating variation of the strain. Yes.
Thank you.
Any further questions? I have one general question that, I mean, does this mean that the theory of superconductivity in iron nitrides is totally different from cuprates, theory of superconductivity in cuprates?
Yeah, yeah.
Yeah,
yes and no. Yes and no. What people say definitely is that we are dealing with an electronic mechanism. Whether I would bet for that, I'm not so sure, but that's what people believe. And both in cuprates and in iron-based superconductors. So we have an electron-electron interaction mediated, for example, by spin fluctuations or by other electronic degrees of freedom. That's the common belief. So, but that's the only thing which is really clearly similar. So in these iron-based superconductors, when you believe what I told you, or when we take this very seriously, that superconducting domes occur not at the magnetic instability, where spin fluctuations are huge, but at the nematic instability, you would say, okay, then could also be that these orbital degrees of freedom are somehow responsible. That's one option. Some people believe that, not all of them. But there are other things. We have this multi-band nature, and this offers a lot of different possibilities of the order parameter. Okay. So we are also, just when you look in the web, you will see two recent papers of us. I was not corresponding author, but we were involved, where we argue that we have time reversal breaking symmetry in the superconducting state. So you have a mixing of different order parameters. You start from an S plus minus, this famous S plus minus thing. You go to a D state. You have mixing of these things. So also the superconducting state of these iron-based superconductors is much richer than it is in the cuprates. So in some sense, cuprates are boring, though people work on that since 40 years now. So it's boring in that sense. You have on a single orbital, phase diagram is always looking at least similar. You always have D-wave superconductors. Okay, very much similar, all the cuprates. In the iron-based superconductors, that's different. So it's really different, and details of the band structure then change also the superconducting order state. And yeah, it's interesting, more complicated, richer, whatever you want.
Yeah. So this is becoming complicated because of multi-orbital or multi-bands near the Fermi level.
Yeah, I think it's both multi-orbital and multi-band.
Multi-bands. So then, if I take these nematic fluctuations are happening because of this multi-orbital. Yeah. Because I mean, if I take like spin fluctuations origin, even in cuprates we have that spin fluctuations.
Yeah, klar. So spin fluctuations is, yeah, okay, that's what even if you have these two parts of the Fermi, or you have one Fermi surface, you can do transitions from one part to the other one via spin flip, and this gives you the spin fluctuations.
Yeah.
So you do not, for spin fluctuations, you do not need necessarily multi-orbitals. Okay, that's a typical instability. And you say, at first glance, you can now go to iron-based superconductors and say we have a whole band, we have an electron band, we have this nesting, and this will enhance strongly spin fluctuations for this peculiar Q-well. This is still a thing which you can argue without taking the word orbitals in your mouth.
Okay.
The orbitals comes in the play when you then realize that, okay, the orbital character of these different bands is different. This will affect this way of spin fluctuations, because going from one to another orbital is less probability than going from the same orbital type. But it comes definitely into the play when you then play with the lattice. And the fact that all these systems then show these structural phase transitions, which is an electronically driven structural phase transition. And actually, there are not many examples. You have charge density wave or something like that, but here going from a tetragonal to an orthorhombic way, driven by electrons. Yeah. That's an unusual thing. That's a nematic transition. This is an electronic instability which leads to the symmetry change of the lattice. This is a nematic transition. And doing that, I think orbitals help. I don't know whether all theoreticians will agree. They could also argue we have this stripe-like magnetism, which breaks symmetry, and the lattice follows. That was the first ideas. But I think meanwhile people agree that this is so prominent here because we have this multi-orbital system. In some sense, so when you compare cuprates, so the superconducting cuprates with these systems, it's similar when comparing the magnetism of simple cuprates with the magnetism of manganites. And manganites, you have all this orbital degree of freedom, then you have the Untitled distortion, you have orbital order, you have much richer phase diagrams. And that's what's happening here with the superconductor as well.
Okay, yeah. Thanks. So any other questions? I do not see any more questions. Then maybe thank you once again. Thank you very much for the nice talk.
No, thank you. I hope very much that we can meet, we both, but maybe with other people also in the audience, where we can meet face to face. We can discuss, we can explain things, either here or at your place. And I'm really looking forward to this soon.
If I may add, Bernd, we are very much looking forward to the possibility of welcoming you in Calcutta. Because, and I do hope that our draft MOU, which is right now with the ministry, that will go through very soon. There's no reason it will not go through. It's just a matter of time. And I do hope the pandemic will come to an end and we'll be able to really welcome you.
Yeah, you have a standing invitation to come. From our side, we agree to everything which we have written. If you want to have some changes, we also will find ways to change it according to your wishes. Yeah.
Thank you.
Okay. Thank you very much for all of you for listening.